All right, so let's pick up where we left off last time. Last time we ended by reminding y'all of what's called Hess's Law. This is what was studied last semester when you studied thermochemistry, when that enthalpy was first introduced. All right, and Hess's Law says that we can combine known chemical reactions as well as their thermodynamic variables to study new reactions. And we said we have these formation reactions where given a compound, we can always draw its formation reaction by taking those elements in our compound and putting them in their standard state as our reactants. They've got this weird balancing where you always keep the product coefficient as a 1. And the reason we like these formation reactions is that a whole bunch of them have been studied, and we have this gigantic table here with all of these thermodynamic variables that correspond to the formation reactions of all these different compounds. So we went on this table and we looked up that delta G value for these reactions. All right, and we found that the delta G reaction for this reaction was 51.3. And remember, because of the sign of delta G, we were able to say that that means that this reaction is non-spontaneous. We looked up the same reaction or a similar reaction, the formation reaction of dinitrogen tetraoxide. We also looked up its thermodynamic variable. All right, also a positive value. But these are our two known reactions here, right? These ones that are tabulated on that constants page. And we want to use them to study this reaction here. All right, so how are we going to do that? What we're going to do is we're going to combine these two reactions in such a way that they sum up to our net reaction here, to our overall reaction. All right. So if we look carefully here, if we summed these two reactions up as is, I would have that dinitrogen tetraoxide on my product side, but my nitrogen dioxide is on the wrong side. All right, it's on the product side up here. It's on the reactant side over here. Okay, so what we're going to do is we're going to take that that second equation rather. We're going to keep it as is. All right, and we're going to need to use this first reaction, but we're going to have to flip it around, right? So instead of writing nitrogen dioxide on the product side and nitrogen and oxygen on the reactant side, I'm going to flip sides here. All right, so now it's going to be nitrogen dioxide on the reactant side, and my two products, that 1/2 nitrogen gas and that oxygen gas. All right, so I had to flip this reaction here. So what am I going to do to the delta G that I looked up? Yeah, so that means that in the opposite direction, the sign of delta G would be negative 51.3, right? So just like we flipped our reaction, we're going to flip the sign of that delta G to negative 51.3 kilojoules per mole. All right, so I flipped the reaction. That means that we're going to flip the sign. All right, and if I look and I added these things up, I still wouldn't get to that overall equation. All right, my nitrogens wouldn't cancel out, my oxygens wouldn't cancel out, and I only have one of those nitrogen dioxides, whereas I need two in my balanced chemical equation. All right, now, so I can't just like throw a 2 out front here and be done with it, or I would unbalance that formation reaction. But what I can do is take the whole thing and multiply the whole reaction by 2. All right, that'll preserve my balancing. So now if I multiply all my coefficients by 2, now I have 2 nitrogen dioxides. 1/2 times 2 leaves me with just 1 nitrogen gas, and then 2 oxygens. All right, and just like I multiplied that chemical equation by 2, I'm going to do the same thing to my thermodynamic variable, my delta G. So I'm going to flip the sign and multiply by 2. So now it's negative 102.6 kilojoules per mole. All right, I'm actually going to leave this as 2 times 51.3 to make a point. Okay, so now if I were to take these chemical equations and sum them up, I'm going to do this the long way real quick just to make a point here. By summing up our chemical equations, that means we're going to, in a new chemical equation down here on the bottom, combine all of our reactants from these two equations. And then in my new chemical equation on the bottom, I'm going to combine all of these products onto the product side. All right, so I just combined all my reactants together into my reactant side of this new chemical equation. Likewise, all my products into a product side of my new chemical equation. And then what do I get to do? I'm going to simplify them, right? And so how do I simplify? Yeah, cancel out things that appear on both sides here, right? So my nitrogens can go, my oxygens can go, and we see that we are indeed left with that overall equation we were hoping to study. Our two nitrogen dioxides becoming nitrogen tetraoxide. All right, and we said our goal was to study the delta G of this new reaction here. Well, just like I was able to simply sum up my chemical reactions to give me my new chemical reaction, I can sum up my delta G values to give me my new delta G value here. All right, so that's my 99.8 minus that 2 times that 51.3, all in units of kilojoules per mole. Okay, and what we would find is that this reaction has a delta G of negative 2.8 kilojoules per mole. All right, so then what can we say about this new chemical reaction that we were just studying here? It is spontaneous. All right, and how were we able to come to that conclusion? We used these two known chemical reactions here, the formation reactions. We looked up their delta G values on that constants page, and we combined them to create this new reaction that we were studying here, our overall reaction. All right, now, that's all well and good. Hess's law is something that I would have made you do kind of the long way a few times in general chemistry 1. That is not on our core here for General Chemistry 2, so we get to simplify things quite a bit here. All right, if we look carefully at the math that we did here to calculate our delta G, we could have calculated our delta G by going to that constants page and simply taken the sum of the delta G of all of our products multiplied by their stoichiometric coefficient. And then subtracted our reactants, the sum of the delta G of our reactants multiplied by their stoichiometric coefficients. All right, and when we do our equilibrium constant, I said there's this one phrase that we're going to like chant to ourselves to get stuck in our head. How do we build our equilibrium constants? What over what? Products over reactants, right? So that stupid little phrase helped us stick in our head, so we always did our calculations correctly. For our thermodynamic variables, we're going to have something similar but a little bit different. We're going to chant to ourselves products minus reactants. All right, it's our products minus our reactants, all right, multiplied by those stoichiometric coefficients. All right, so why did we do all this Hess's law business? Hess's law is what allows us to take those known reactions and combine them together. We can kind of simplify things into this equation here. So this is what Hess's law has given us here. We go to our constants page and we look up those thermodynamic variables for our formation reactions, and we can do our products minus reactants in order to get those values. All right, so we just did it for delta G. Let's use our simplified equation here. This equation works for any of the thermodynamic variables. If you went in and replaced all these G's with H's, that'd be your equation for enthalpy as well, right? So it works for any of those thermodynamic variables. So let's take our chemical equation here. All right, and I'm going to go to the constants page and I'm going to look up the entries for our products and our reactants. All right, the N2O4 gas. Here's this one. All right, I need the same thing, but for just nitrogen dioxide. There we go. Cool. All right, and just as a reminder, the order of these values on our constants page, that very first column is the delta H. That second column, the delta G, which we already calculated. And the third column is that entropy. All right, so everybody take a second. We'll work together here. Calculate delta H, and I'll calculate delta S. All right, so my product delta H is that 9.16. I'm going to subtract my reactant multiplied by its stoichiometric coefficient. All right, so we should have gotten an enthalpy change of 57.24, or 57.2 if we're rounding to the correct number of sig figs, kilojoules per mole. All right. Similarly for our delta S, 304.4, products minus reactants, that 240.1. I get negative 175.8. All right, and we want to note here, this is going to be kind of a little bit of a thorn in our sides here, but it's just the way that we have to deal with our constants page. Our units for entropy are listed in not kilojoules per mole Kelvin, but joules per mole Kelvin. All right, so we're going to have to do some unit conversions here. All right, so what can we say about this reaction? We said that our delta G was negative, so we knew it was a spontaneous reaction. What is our delta H telling us? That this reaction is exothermic. It releases thermal energy. All right, and what about our entropy? Is this entropy good or bad? Right, so negative entropy is bad. This is entropically unfavorable. And let's look at our chemical equation and see if we can't figure out why that would be. Why would this reaction be entropically unfavorable? Exactly, right? It's a number of particles thing. We have two gas particles over here on the left, and they're being combined into just one bigger gas particle. That is entropically unfavorable. We're creating more order in that process. Cool. All right. And so we got these three thermodynamic variables that we can calculate here. Let me just put the other one down. The first one we did, that negative 2.8 kilojoules per mole, telling us that this reaction was spontaneous. Okay. So if we go to our constants page here. So, I mean, this is actually something that's, thank God for Hess's law. It really makes it so much easier to study all these other chemical reactions based on just these formation reactions here, right? These values that we get from our constants page. If we can find our reactants and our products on this constants page, then for any chemical reaction, we can figure out whether or not it's going to be spontaneous or non-spontaneous, whether it's going to absorb or release thermal energy, what its enthalpy is, and whether or not it's going to be entropically favorable or unfavorable. Oops, not there yet. All right, so these three pieces of information, we can use that constants page and we can find as long as we can look up those products and reactants. Cool. All right, so I know everybody's super pumped about that. Brand new tool to let us study all these chemical reactions. All right, so first thing first, we're going to talk. We've talked before about a certain value that allowed us to say whether a reaction favors the products or the reactants, and we could even see how strongly it favored those products or reactants. What was that value? Equilibrium constant, right? So now we're talking about this spontaneous, non-spontaneous business. Well, it turns out that there is a direct relationship between delta G and our equilibrium constant. All right. It turns out that that equilibrium constant, KEQ, is the same thing as e to the negative delta G over RT. All right, so if we do some math here, what we could convince ourselves of is that if delta G was less than 0, one of our spontaneous reactions, well, then that would necessarily mean that our KEQ was greater than 1, which we said was a reaction that favors the products. So saying you have a negative delta G is the same thing as saying you have a reaction that favors the products. Both of these are one and the same pieces of information. Likewise, if you have a delta G that was greater than 0, what we would call a non-spontaneous reaction. That means that your KEQ is necessarily going to be less than 1. Right? So a non-spontaneous reaction is the same thing as saying a reaction that favors the reactants. All right, so because of that, that term non-spontaneous can be a little misleading in certain situations. It's helpful to sort of remember that it really means that the reaction favors the reactants. So when we say non-spontaneous, we mean it's going to be spontaneous in the reverse direction. All right, so let's just do this calculation for that reaction that we were studying. We're going to note here that R is that ideal gas constant, that 8.3144 joules per mole Kelvin. And our T in this case, we're going to use room temperature, or 298 Kelvin. We'll talk a little bit more about temperature here in a minute. All right, before our reaction that we just studied above, using Hess's law that gave us our products minus reactants formula, tell me what the delta G, what the equilibrium constant is for this reaction. All right, and you're going to note that pain in the butt mismatch of units between our units of delta G, which is kilojoules per mole, and R in joules per mole. So be mindful of your units when you're setting up your calculation. All right, so I plug in my delta G, my 2.8, my negative 2.8 kilojoules per mole, which when I multiply that by -1 gives me positive 2.8 kilojoules per mole. I'm going to divide that by R times T, but again, what we want to note here is we got a units problem. Moles cancel out, Kelvin cancel out, but I got kilojoules and joules here. We need to square away our units, so I'm going to insert in here a joules to kilojoules unit conversion, right? Using the fact that there are 1,000 joules in 1 kilojoule. All right, punch that into our calculator. We get 3 points. We'll just round this to 3 sig figs here. All right, and so we can conclude from our equilibrium constant that negative delta G value gave us a KEQ greater than 1. In this case, we can say it weakly favors the products. All right, so we have this relationship between our equilibrium constant and our new thermodynamic variable, our delta G of our reaction. All right, they're linked together through this equation here. All right, let's go back to our example here of our dinitrogen tetraoxide and these 3 thermodynamic variables that we solve for. Okay. We figured that this was spontaneous based on that delta G calculation, that it was exothermic but entropically unfavorable, a reaction that created order, not disorder. Well, if we remember, we made this little cheat sheet of the signs of delta H, delta S, and delta G, and how they were all entangled in one another. And for a reaction that is exothermic but entropically unfavorable, we found that that reaction would be spontaneous, but only at low temperatures, that there was a temperature that you could crank this up to where that reaction would no longer occur. All right? So when we calculated the delta G here, indicating that this reaction was spontaneous, well, where are we in our whole temperature thing? All right? There's something that I've been glossing over up until now, and that is if we look on our constants page, our delta H, delta G, and entropy values all have this little knot next to them. All right, and this is specific to a set of conditions which are known as standard conditions. All right, so we're going to be good, and we're going to go back. What we calculated using our delta H naught, delta G naught, and delta S naught, right, were these standard free energy, enthalpy, and entropy values. Right, and that little knot there, that little circle up top, indicates that this reaction, that these are true for a reaction that's carried out under standard conditions. All right, so it turns out that yes, this reaction is spontaneous as long as you carry it out under a specific set of conditions known as standard conditions. All right, and the first important part about standard conditions is that it dictates the temperature at which that reaction is conducted must be 298 Kelvin, all right, or about 25 degrees Celsius. Okay, so yes, the reaction is spontaneous as long as you're carrying it out at that specific temperature. So according to our little cheat sheet here, at some point I could raise the temperature and it would no longer be spontaneous. So how do I figure out my thermodynamic variables at any other temperature? All right, so we want to calculate delta G at any temperature. All right, so if I want to change my temperature, I can't use this delta G value from my table anymore. Delta G is incredibly sensitive to temperature. This value that I got from my table is really only good at that standard conditions temperature. So if I want to figure out delta G at any other temperature, we got to go back to that chemical potential formula that we derived, where our delta G is equal to delta H minus T delta S. All right, and if we want to calculate delta G at any temperature, okay, we can estimate it by using those standard thermodynamic variables for enthalpy and entropy. Our standard enthalpy and our standard entropy. All right, now this is just an approximation because enthalpy and entropy also depend on temperature, but not nearly as much as delta G does. So we can get a pretty good idea of what our delta G is using our standard enthalpy and standard entropy values. All right, so let's ask, is the reaction still spontaneous at 350 Kelvin? All right, so everybody take a second using our thermodynamic variables that we found earlier. Tell me whether or not the reaction is still going to be spontaneous at this higher temperature. All right, if we start plugging in values here, our delta G is that enthalpy value, that 57.24 kilojoules per mole, minus our temperature, 350 Kelvin, times that delta S value, which was negative 175.8 joules per mole Kelvin. All right. What's wrong with my problem here? My unit's awesome. All right. Yeah, same problem that we saw before. We got to watch out. We can't combine kilojoules with joules. Doesn't work, right? And since we like to report delta G in kilojoules per mole, we're again going to convert using that 1,000 joules in 1 kilojoule. All right, now my joules cancel out, my kelvins cancel out, and I'm left with joules per mole in both terms. So my delta G here at this new temperature is going to be 4.29 kilojoules per mole. And what can we say? At this new temperature, is our reaction still spontaneous? No. Now our reaction is non-spontaneous. All right, so we showed that for a reaction that was exothermic but entropically unfavorable, we could find a temperature high enough where that reaction is no longer going to be spontaneous. This reaction was spontaneous at room temperature according to that standard free energy value. But when I crank up my temperature to 350 Kelvin, about 70 degrees Celsius, all of a sudden now the reaction no longer occurs spontaneously. All right, so we can use this relationship here to our advantage, right? We're sort of changing our temperature and seeing how our equilibrium constant, or rather our free energy values change. All right, this is particularly useful if we're studying phase changes. All right, so let me grab, we're going to take this chemical equation, we're going to use water. We got these values from our constants page here. All right, and if we're going to take water from this liquid state to the gaseous state, what are we doing to that water? Heating it up, and then it's going to start to, so we would call this boiling or vaporization if we really wanted to be fancy about it. All right, so let's go ahead and calculate the delta G naught, the delta H naught, and the delta S naught for this process here, for this phase change. All right, but before we do that, before we actually do the math, let's see if we can't predict what these values should be based on what we know about these thermodynamic variables here. All right, so delta G is going to tell us whether or not this reaction will happen here, okay? So this boiling reaction at room temperature, are we worried about water boiling? No, right? So we would expect that this reaction would be non-spontaneous at our standard conditions at that 298 Kelvin. All right, what about the enthalpy here? Enthalpy for a random chemical reaction is hard to predict, but for these phase changes, they're pretty predictable here. To go from the liquid to the gas state, the big difference is the amount of kinetic energy that those molecules have. Are those liquid water molecules going to have to absorb heat or release heat to get kinetic energy? They're going to have to absorb it. And what do we call when we absorb heat? That's an endothermic process. All right, and then lastly, if we're going from liquid to gas, are we creating more order or disorder? Disorder, so we would think that this would be an entropically favorable process. Cool. All right, so everybody take a second. Calculate these thermodynamic variables, our products minus reactants, given our table here. All right, so our delta G that we calculated was 8.5 kilojoules per mole. Indeed, this would be non-spontaneous. Our delta H is positive 44.0 kilojoules per mole. So that is endothermic. And we get a positive value for, our entropy, meaning that it is entropically favorable. All right, but again, this is at standard state, at that 298 Kelvin. All right, if we look any reaction that is endothermic but entropically favorable, it might be non-spontaneous at low temperatures, but if we increase the temperature, that will spontaneously occur. All right, so we can just start guessing and checking, plugging in values and seeing if they're positive or negative. All right, but what we're going to use is the fact that at that phase change temperature, the liquid and gas states are in equilibrium where the delta G is equal to 0. All right, so what does that mean? Well, if we look at our formula here, we have this way of approximating delta G at other temperatures. All right, and if we plug in our boiling temperature here, right, where we have delta H naught minus that boiling point, so I'm going to label that TB times delta S naught. Well, if I'm at that boiling point, if I'm at that phase change temperature, then my delta G is simply equal to 0. And since we know what our standard enthalpy and standard entropy are, we can solve for that boiling point, right? We can rearrange this equation and use this equation to predict the boiling point of a substance. All right, so everybody take a second. Given our equation here, rearrange it to solve for that boiling point temperature. Again, when you're plugging in values, pay attention to your units. right, so we punch this into our calculator. I'm going to note that I have this unit conversion on the bottom here to square away my energy units. All right, I get this 370, we'll leave it there, Kelvin. All right, or if we wanted to use our Kelvin equals degrees Celsius plus 273.15 conversion from our constants page, we could subtract that 273.15, and this tells us that the boiling point of that substance is 97.2 degrees Celsius. All right, so importantly, when we rearrange that equation for delta G equals 0, all right, we got this equation here. Our boiling point is equal to delta H divided by delta S. We plugged in our values, and we got our predicted boiling point here in Kelvin, which we then converted to Celsius. Okay, now we're talking about water. This is a substance that we know well here. What is the boiling point of water? 100 degrees Celsius. And what did we calculate it was? 97.2. So did we hit it dead on? No. Okay. Importantly, we're still estimating this by using our standard enthalpy and entropy because they do change a little bit with temperature. Those are the standard values. Those are what are true for 298 Kelvin. They're going to deviate a little bit as we change our temperature. Nonetheless, we get pretty close, right? So this is a way to approximate our our boiling point of our substance. And for water, why would we do that? Well, we didn't really need to. But of course, there are plenty of things on this constants page. Bromine, for example, is one of those weird elements that's a liquid at room temperature. One of only 2 elements, right? I don't know the boiling point of bromine off the top of my head. So we could use our thermodynamic variables from this page here to figure out what the boiling point of that substance is, or to estimate what that boiling point is. It's not going to be perfect, but again, it'll get us in the right ballpark. Cool. All right, so one last thing here. Let's go back to our first example that we did here of our nitrogen dioxide being converted to dinitrogen tetraoxide and all these thermodynamic variables that we calculated here. And everybody was like, wow, that's the coolest thing I've ever seen in my life, that you can actually find out all 3 of these pieces of information just by using that information on the constants page. And then I said, well, wait a minute. That's actually only under standard conditions, meaning it's at a specific temperature. And everybody was really disappointed until we found out that we can predict what it is at any temperature using this equation here. All right? Now, it turns out that standard conditions are even more stringent than just a temperature requirement. It also tells you how much of your product and reactant you have in your reaction mixture. So standard conditions is that 298 Kelvin. It also means that any gases have a pressure of 1 atm, and any solutions have a concentration of 1 molar. All right, so what this delta G value right here is saying is that yes, this reaction is spontaneous if we were to mix 1 atm of nitrogen dioxide with 1 atm of that dinitrogen tetraoxide, right? We combine those in equal amounts. Yes, the reaction will spontaneously proceed in the forward direction. Right? That's what that calculation is really telling us. It's specific to the amount of substance that's in there. Okay? And again, for gases, that implies that all of your gases have a pressure of 1 atm. So again, kind of a bummer because that seems really restrictive then, right? Well, like, is it spontaneous when I have any other pressure of gas? What if I start out with an unequal mixture? All right, so again, don't worry. I know you're all bummed out. We have a way to deal with it. All right, we can calculate delta G for any initial conditions. All right, and so what they did was they sort of took advantage of this relationship between the equilibrium constant and our delta G. We can then start to use this thing that we used in that equilibrium chapter where we plugged in our any conditions, all right? And that is that reaction quotient Q. All right, remember that this is just your equilibrium expression, but with non-equilibrium values. This is when you can plug in anything you want. All right, but when you're building that Q, you're still going to remember to yourself, just like with equilibrium expressions, products over reactants. Right? Q's that same thing. All right, so our equation that we get when we do some fancy math here is our delta G under any conditions is going to be equal to that standard condition delta G, that delta G naught, plus RT natural log of Q. All right, so let's go back to our, we'll just copy and paste this chemical equation again so we can build our equilibrium expression. Sorry. Okay, we can note we calculated that delta G naught of negative 2.8 kilojoules per mole. Okay, and so now we want to ask, is the reaction spontaneous? If 0.5 atm of nitrogen dioxide is combined with 5 atm of dinitrogen tetraoxide. All right, so everybody take a second. Using our new equation here, again, we talked about that ideal gas constant, that 8.3144. We're still at our standard temperature here of 298 Kelvin. All right. I want you to calculate Q and then use this equation here to tell me whether or not this reaction is still spontaneous under this new initial set of initial conditions. No, because, well, anytime we're talking about thermodynamics, we have to use Kelvin. But also you could tell because the units of R is that joules per mole Kelvin, right? So you got to square away those units. All right, so my value of Q here will be 20. I did my products over my reactants. I had to turn that stoichiometric coefficient into an exponent here. So to calculate Q, I took my pressure of my product divided by my pressure of my reactant squared. All right, so if I set this up where I plug everything in, my delta G minus R K natural log of Q, I'm going to again just have to note I got a units problem here. So I need to squeeze in a unit conversion from joules to kilojoules. You add them, I'm sorry. Yeah, noted my original equation. All right, so punch that into my calculator, right? Along with that joules to kilojoules unit conversion, we get 4.6 kilojoules per mole. So under these conditions, what would we say about this reaction? Non-spontaneous, and really this means that this reaction will proceed in the reverse direction, right? So remember, by non-spontaneous, that's just another way of saying it's spontaneous in the reverse direction. Cool. All right, so first of all, we kind of formalized how, given a chemical reaction, we can calculate all these thermodynamic variables, our delta G, our delta H, and our delta S. And then we talked about how our delta G was related to our equilibrium constant through this equation here, right? And really, if we're good, we want to put in, we hadn't learned about this yet at the time, but we just want to put it in here, that it was delta G naught that we plug into this equation here for our equilibrium constant. Right, that standard free energy will tell us our equilibrium constant. So calculating that delta G from our constants page, we could also calculate the equilibrium constant of those reactions. We talked about that little knot and how that knot meant that it was under standard conditions. Standard conditions will tell us whether the reaction is spontaneous, exothermic, entropically favorable or unfavorable at 298 Kelvin. If we want to change the temperature at all, delta G is really sensitive to temperature, so we can't use that standard value anymore. And instead, we have to use our relationship between delta G, delta H, and delta S. Using those standard values for enthalpy and entropy, we can approximate the delta G at any temperature. And we use that, took it a step further to talk about specific chemical processes called phase changes, where at that phase change temperature, our delta G is equal to 0. So setting that equation equals to 0 allows us to solve for that phase change temperature, which means that we can predict boiling points based on our thermodynamic constants as well. All right, and then the last aspect of standard conditions was that it's a really specific amount of substance that you're starting with, either 1 atm of all gases or 1 molar of all solutions, right? So it's a very specific set of conditions that tells us whether or not our reaction is going to be spontaneous. If we want to go outside of those standard conditions, we can figure out whether or not the reaction is going to be spontaneous or non-spontaneous using that reaction quotient Q, right? So this equation here will allow us to predict whether or not any set of initial conditions will proceed in the forward or the reverse direction, okay? Similar, that was exactly what Q was telling us before, but now it's in this unit of free energy here. Cool. All right, that's all I got for y'all for our thermodynamics discussion. Okay, so we will break and meet for lab at half after.